Okay, other questions? Oh, yes.
Equation sheet.
No, I don't allow equation sheets. Well, so I'll tell you a little, look at my old exams, you'll see the structure. About 40 to 60%, 40 to 50%, something like that, will be short answer. So I expect you to remember certain definitions, right? If it's something that I put on the board, right? What does it mean to be linearly independent? What does it mean for a matrix to be symmetric, or, well, we haven't talked about that, but what's the transpose of a matrix? Things like this. The rest of it will be more like quiz problems, but I don't think it's difficult. I think we've, got to give some steps or whatever. So you have another question?
It's the best way to prepare for this type of questions. Over quiz.
Yeah, yeah, I think that's the best way. It's just like exercising, but you got to gym a lot, that kind of thing. So, yeah, come to the review session if at all possible. We can talk about this kind of thing. So, others. Okay, so we were going to talk about today. So you can find this material mostly in section 2.5. We're going to talk in particular about what they call LU. By the way, your quiz is due Tuesday. I just posted this morning, but you will not need what I talk about today for that particular quiz. You might need it for Fridays, but so in theory, I did some cogitating over the weekend about what I wanted to ask you. In theory, you could have done this Friday, so you don't need to. Yes.
The quizzes that are due on Fridays, will we ever need the material from that Friday to do the?
I will never post a quiz before you're ready to take it.
Okay.
Right, so that's kind of my basic thing. Now, that's not to say that, if I post it like today, if I posted it at 6 in the morning or whatever it was that I did, I wouldn't take it then, because why would it hurt for you to listen to more material? That's only gonna help, but But yeah, I won't post it till you're ready to take it. Okay, so. In many applications, linear algebra. Solve equations. And we've solved equations like this. Right? This is old school, right? This is the old augmented thing. You make your columns and then you augment with this and you go through row reduce and solve things, right? But what if you have more? What if you've got a boatload of equations like this you have to solve, right? So lots of times you're solving things in business or computer science or any of the sciences really, and you have sort of the same coefficients, but you get different outcomes that they can be, and you have to repeatedly solve this equation, right? Now, I'd really rather not do full row reduction every time, because that could be a pain in the butt. This is like, 25 by 360 matrix, right? This could be a bit of a mess. Now, one thing that you can do to solve this, one of the ways you do it is maybe you find A inverse and solve them all like this. If you know what A inverse is, then multiply this by A inverse and you get X is A inverse B1, and you can just go through and solve this like a little magic box, right? But I did say maybe what problems might we encounter? Right, for a couple of big reasons. So Adam's answer sort of incorporate a number of things at once. Number one, A may not even be square. I might have a different number of variables, different number of equations. It might be a 25 by 50 matrix, right? And then there's no way you can do that because what has to be true for a matrix to be invertible? First and foremost, it's got to be square. No other way around that. If it ain't square, you can't invert it, right? So, and I would think that in many applications, matrix might not be square. I mean, why would there be the same number of variables as equations you have? Probably not. And number two, even if A is square, it's still may not be inverted. In fact, I suspect in many applications this would be true. I mean, you may have the same number of equations as variable, but it still may not be inverted, right? And in either case, there is no A inverse, none at all. So doing this is a hopeless task. Now, again, what you can do with this collection of equations is, well, you can put this in a matrix and row reduce it, and then you can put this one in a matrix and row reduce it, and so forth and so on. But is there a quicker, less time consuming way to do this? And the answer is allow you to solve this in general more quickly. In fact, sometimes depending on what the matrix looks like, it can significantly lower the time, the computation time taken. Okay, so what is an element factorization? So what is one of these? I'm gonna tell you what an LU factorization is. And then I'm gonna try to sort of justify this thing about why it would, because after all, what I'm gonna do is I'm gonna write the matrix in a product of two matrices. Why does that make it easier? So if A is an N by, I'm sorry, M. An LU factorization. By the way, just to help you remember, L means lower and U means upper. Is an LU factorization of A. This is a factorization of the following. Here's your matrix A, which is N by N. Lower, and this is upper. Now my lower matrix is going to be square. And so it's going to be M by M. So it's got the same number of rows as a, but perhaps a different number of columns. What size does U have to be? This has to be, U and A are the same size, right? And L is lower triangular. So L is something like this. With ones. So it's always gonna be lower triangular square and one's on the diagonal. Zeros above the diagonal and some to be determined numbers in the lower, below the diagonal. And U is echelon form. Of so what a LU factorization of A is it is just a is whatever A is, it is a M by M lower triangular times an M by N upper triangular. Let me give you an example. I'll just kind of write this out and then I'll derive it. I'll show you how you can actually build these things from scratch here. Matrix here. 2, -4, 4, -2. This is 6 months. 3. And -1, -4. 8, 0. This is by A. So it is a 3-row by 4-column matrix. As it turns out, so I'm going to pull this out of some strange orifice, but when this is over, I'm going to show you where I got this. Right, I'm going to show you how to get this from scratch. Let me just verify the formula first. Okay, I know my L has to look like that. It has to be square. It has to have zeros above the diagonal and some to be determined numbers down here. Now, where I got these numbers, I'll show you in a moment, but here's what they are. 3 -1/2 and -2. And here's the echelon form. Um, 0, 3, 0, 0, 0. Notice this is echelon form. It is not row reduced echelon form, right? It's not row reduced, but it is echelon form. 1 pivot, 2 pivots, 3 pivots. Agreed? Now, of course, if you guys see what I do to row reduce echelon format, right? I turn that into a 1, turn that into a 1 and take that out. And I turn that into a 1 and take columns above it out. Right? Now, let's check this works. If you multiply this times this, I'm going to basically get the same first column. Everybody cool with that? So that works. So it works. This is going to be, this row times this column is going to give me a 6. That's good. That's going to give you -12 and 3 is -9. That's good. That's going to give you 12 -5 is 7. That's good. That's going to give you -6 and 3 is -3. Good. So good to go all the way down to 2 rows. Let's check the last one. This row times this column is going to be a -1. That's going to be +2 minus 6 is -4. Good. That's going to be -2 plus 10 is 8. Good. And that's going to give me a 1. -6 is -5 plus 5. So everybody, okay, that factorization works. Now, let's just leave that LU factorization for, I'm not gonna tell you yet where I get it, but why would this help, right? Well, here's the computation idea. The idea is solving this, assuming these are our coefficients in the augmented matrix, solving this, I'd have to row reduce it every time. All right, I have to go through the row reduction, and you know, I'll have this other column that has numbers in it that will do complicated things with that. All right. If A is LU, then what I have, this equation is AX equal B is now LU X is equal to B. So this inspires me to solve 2 systems. And then if I call this Y, UX is Y, then LY is equal to B. So let me ask you all this. I've turned solving 1 equation into now solving 2 equations, right? It seems a little counterintuitive, doesn't it? I'm saying, oh, look at me, I'm so smart, I can do this quicker by letting LY equal B and then UX. So I find my X by first putting in B for this and finding Y, then putting in Y here and finding X. So now I've turned a 1-step process, just row reducing this, to row reducing B to get Y and then Y to get X. Why in the world is that going to be any better? Anybody see? Right, I'm doing 2 things now instead of 1, right? This doesn't seem like things have gotten better. Or have they? Well, I guess if we were going to go back, the first thing I'd have to do is find Y by doing this equation here. Somebody tell me why solving LY equals B in this matrix is easier. It's empirical. Actually, that's a good observation. In fact, it turns out this is empirical because it's always going to be a square matrix if one's on the diagonal. But even if I didn't know that, these equations are very simple, aren't they? Right, the first one is x1 is whatever's up here. And then the next one is 3x1 plus x2 is what over here, but I already know what x1 is, so bang, I've solved that. And the next one is minus a half minus 2. Well, I know what these 2 numbers are, equals x3, and I've got that. The fact this matrix is triangular means that basically I'm just back substituting, so it's just a quick process like this. So this should give me very quickly what my y is. And now I put my y into here, and it's the same thing. If I had an augmented thing with y1, y2, y3, it's immediate what y3 is, right? Or what the appropriate x is, you just divide y3 by 5, right? And now I know what that is, and so I've got a free variable here, but this will give me my y2 because I just divide by this, and now I've got my y1. It's the same principle, right? even though I'm doing two things, all the zeros in here and the fact that these are, triangular matrices, got a lot of zeros in it, actually makes the process quicker. Sometimes it significantly, improves the speed. Okay, well, good for us. Now you can take a matrix and you can get an LU factorization. You have to do some slightly more subtle stuff, so this is all predicated. In all my examples, I am going to assume that I can reduce this to echelon form without swapping any, rows. But actually swapping rows here corresponds to swapping rows here, so you can actually generalize this a bit, but I'm not going to get too much into that. Let me show you how to do LU factorizations. So there's my justification for why it's quicker. Solving the triangular matrices, even though there's two of them, is oftentimes quicker. And so the idea behind LU factorizations, the idea behind where to do it, is you do the row reduction that you would do for A once, and it's sort of recorded in this right here. So let me go through this. So how do we get it? Okay, so I'm gonna, here's Jim's practical guide. Now, again, in my examples, I'm never going to do a row swap, right? It'll always be either, in fact, the only thing I'm gonna do is I'm gonna add scale and multiple one row together. So let's take this one apart. 2 minus 4, 4 minus 2, 6 minus 9, 7 minus 3, minus 1 minus 4, 8, 0. Now, what I'm going to do is I'm going to start here doing row reduction, and I'm going to kind of record, because that's essentially what the LU does. The U gives you your final echelon form, and your L sort of records what it took to get there. Okay. So I'll do a few examples, so maybe we can get our sea legs here. It's good to kind of start off here. What's the size of, what should L be? Size wise. Right, it's the number of rows, in this case 3, and it's going to be square, so it's going to be 3 by 2, right? I know that much. So guess what? I'm over halfway there. How about that? I already know that much, except that crazy enough with these zeros here, that I don't know. But this much I know, right? I've got 6 ninths of this matrix already. All right. That's my first pivot. Everybody agree with that? Basically, this first row corresponds to this first pivot. It should be 1, 3 minus a half. Notice what have I done? I've taken this row and I've cut it in half so that I start with 1. Everybody agree with me? Now, let's row reduce this. What would I do to row reduce it? I would use my little pivot element to take out, make zeros here. Everybody agree with that? So let's do this. So I'm going to multiply by -3 and add to the middle. And I get 2 minus 4, 4 minus 2, 0, 3. That's minus 3 and add is minus 5. Times, so that's going to be 6 minus 3 is 3. And multiply this by, I guess, times 1/2 and add. So I can take that out. So I'm going to get 0 here. let's see, times 1/2 is -2 and -4 is -6. Yeah, better check on this. This is 2 and 8 is 10. And 1/2 of this is -1 and 0 is 1. Everybody okay with that? Okay, so where's my second pivot? Here it is. This is the pivot element. Everybody agree? That's the second one I come to. And so that's gonna go right here. I need to multiply this by 1/3, right? I is 2, so that's gonna be like 1 minus 2. Right, okay with that? And now I've got my L, but I need to get all the way down to echelon form here. Let me reduce one more time. This is the 2 minus 4, 4 minus 2, 0, 3, -5, 3. Now to take this out, I'm gonna multiply this by 2 and add. So it's gonna be 0, 0, 0, 5. And of course, there's your last pivot, which we would divide that by 5 to make it a 1, and it's already there. I already put that in. So notice, there's my other factor. What sort of putting the lower part of the pivot column in, what it's doing is it's recording the row operations that made this work. Okay, everybody okay with that? Don't worry, we'll do more. Yes, sir.
Can you explain again how you knew where to put, like, those numbers in L? Like, how you knew where to put, like,
So this comes, basically think of it this way. This is the first pivot column scaled so that the top thing's a 1. The 1, 3 minus 1. Right? Okay, do your magic until you discover where the second pivot is, right? The stuff above it doesn't matter. This is the second column of L, again with that scaled down, 1 minus 2, and there, right? Do your magic again, and here's your last pivot, and that's the last column scaled down, right? Does that make sense?
yes, thank you.
I think it may be able to clear up a little bit if we do like a couple more numerical examples. Do another one. How about this one? How about one off the other extremes? Let's A this. 2 minus 6, 6 minus 4, 5, 7, 3, 5, -1, minus 6, 4, minus 8, and 8 minus 3. Okay. Right, this would stretch you in the other direction. Well, what size is my L got to be here? Okay, this one's gonna be kind of funny, so I'm gonna ask you guys what you think. I'm gonna run out of real estate here. This has got to be 5 by 5. What's the first column? There's the first pivot element right there. All right, everybody good with that? So the first column should essentially be this. Scaled down so that I've got a 1. That should be 1 minus 2, 3 halves, minus 3, 4. Everybody cool where I got that? Okay, so let's row reduce this. Small. 2 6, 6. Okay, multiply by 2.5. So that's gonna be 0 minus 7. 5. Multiply by -3/2 and add 0. Let's see, times -3/2 is gonna be 9 and 5 is 14. -3/2 is -12. I'm sorry, -9, -1 is -10. Okay, multiply this by 3 and add. And that's going to be 0. -18 and 4 is -14. 18 minus 8 is 10. And finally, get the bottom one. I'm going to multiply this by -4 and add 0. That can be 24 minus 3 is 21. It's going to be -24 and 9 is -15. Okay, here's the big test. By the way, somebody identify what should my next, of course, obviously it's got a 0 here, and this should be a 1, but can anybody fill in the rest of that column? Any ideas? Yeah. Yeah, that's right. What you're doing, this is the next pivot. You scale this so that's a 1, so it should be -2 plus 2 negative. Right, okay with that? Now, we're going to use this to kill all the stuff below it. Let's see. I'm going to multiply this by 2 and add. -7, 5. Multiply that by 2, I get 0, 0. When I multiply this by -2 and add, I'm going to get 0, 0. And finally, I'm going to multiply this by 3 and add. That's going to be 0, 0. How many pivots do I have, by the way? I just got 2, don't I? Oh dear, I've run out of columns, haven't I? Right, I've got. Those are the 2 pivot columns I got, right? And now I'm out of gas. So what do? Oh, that's with zeros. That's right. Actually, you can fill in anything you want. 7 power 3, a million, whatever. You can do anything you want, and it will work. And you know what? Anything I like, his idea, zeros. And this is all because this is already an echelon form, right? Check it, it'll work, right? This row comes this column, this row comes this column, this row comes this column. That gives me the 266. This row comes this column, gives me -4. This gives me 12 minus 7 is 5. This gives me -12 plus 5 is -7. This row comes this column. By the way, notice here's where I kind of started filling in crap that I didn't care about. Can somebody tell me why it doesn't matter? Why do all these entries? So I filled these in. I said you could fill in anything you want. I put in zeros because I thought that was a pretty good choice. Why do these not matter? Because they're being multiplied by. When you take these rows times this column, these entries all fall below where there's any non-zero entries. So it doesn't make any difference at all. But I can put anything here and it's not going to change the factorization. So you might as well put in zeros. Yes.
So with the third column, because in like the one that starts with 2, -6, because they're all zeros, it doesn't matter.
The third column here, right, is what now?
What's under, it doesn't matter, but if they weren't zeros, It would.
Well, if there was another column, there's only two pivot columns here, right? And by the time we hit three over here, there's no more pivot columns. So these have to be zero by definition, and that has to be a one. What's below here? Anything you want.
And so if the column wasn't 65000, it would matter, but only the,
Oh, yeah, this does matter in the factorization, but the entries over here don't affect the computation at all. Right, is that clear? So yeah, multiply this out, and you'll see exactly what you need. Let's do another couple, please. All right. Let's do this one here. Four. 2, 4, minus 1, 5, minus 2, minus 4, minus 5, 3, minus 8, 1, 2, minus 5, minus 4, 1, 8, and minus 6, 0, 7, minus 3. Okay, so my L for first pivot column I come to. Right? You scale this thing so it starts with 1, so that it's divided this column by 2. 1 minus 2, 1 minus 3. Did I get this so far? Okay, so let's clear out this column. We get the next step, sort of for the echelon. It's going to be 2, 4, minus 1, 5, minus 2, 0. We'll see a multiply by 2 and add. So it's going to be 0, 3, 1, 2, minus 3, 1, 2. Yeah, that's right. Multiplies by negative 1 and add, and that's going to be 0, minus 9, minus 3, minus 4, and finally multiply this by 3 and add, and that's going to be 0, 12, 4, 12, and minus 5 like this. Okay. Somebody tell me, what's the next column? There's, I'm forgetting the 0. Yeah. 0, 1. 0, 1, what's the next two? 8, 3, 4. Right. You're keying on this now. Scale that 3 down to a 1. 1, negative 3. If I agree with it. Keep going with this. Minus 1, 5, minus 2, 0, 3, 1, 2 minus 3. Okay, so I'm gonna multiply this by 3 and add, so that's going to be 0, 0, 2, 1. And I'm gonna multiply this by minus 4. Multiply by minus 4 and add 0, 0, 0. That's going to be 4 times 12 minus 5 is 6. Okay, somebody tell me what's my next column. L. Good. What you're doing now is you're keying on this. This one's skipped because it's not a fifth column, right? So go 2 down, that's 1. And now I know what the last one is, it's gotta be 1, but let's finish this off. Here's the U. 2, 4, minus 1, 5, minus 2, 0, 3, 1, 2, 3, 0, 0, 0, 2, 1. And I'm gonna use this 2 to take out that 4, multiply by minus 2, take it out, 0, 0, 0, 0, 5. So here's the last bit right here. As it should be. Multiply L by U, you will get back to the original matrix. Okay. Any questions on that? All right. One more. A little bit. One. 6, 4, 15 minus 10, 1. 2, 0, okay. This is 4 by 3, so my L should be 4 by 4. Ready? Okay. Okay. First column. Scale down, of course. 1, 2, 5. I agree with you. Okay. So let's take out what's below. 3 minus 2, 1 comes 2. Thank you, see that is math. It's going to be 0, 0, 2. Times, for this one times -5 and add, that's going to be 0, 0 minus 4. 3. And here I've already got a 0 here, so I'm gonna leave that. 6. Okay, so what's my next one? So the next pivot is actually here. Got that. I agree. which 0, scale it down, 1 minus 2. Now, work your magic here. But this one's kind of easy, right? Because this row's only got that 2 in it, so I can take everything below it out. 3 minus 2, 1, 0, 0, 2, 0, 0, 0, 0, 0, 0. So what about the rest of this? Doesn't matter. Those entries are all forced by the form of the matrix, right? You gotta have zeros above and you gotta have ones on the diagonal. This thing, anything you want, right? You can make this Mickey Mouse, it doesn't matter. Make it 0, but you can make 9 or 8, 6, 7, 5, 3, 9, whatever you like. And it will work. Okay, any questions on that? Yes, sir.
Can you explain again why those last values you just put in the L matrix can be anything?
Well, you have to put in zeros here because it has to be, you understand why you have to put zeros above the diagonal, right? Because that's just, it has to be in that form, one's on the diagonal. This one, in fact, let's do this. Let's call this Fred, because it doesn't matter what we put there, right? Now let's see why this works. I think it's a good thing to see why hopefully it worked for us. If this works, I should be able to multiply L by U and get the original matrix, right? So L is 1, 0, 0, 2, 1, 0, 0, 5 minus 2, 0, and 0, 3, Fred, 1. And then you multiply by the U we got, which was minus 3, 2, whoops, 3 minus 2, 1, 0, 0, 2, and the rest is this orgy of zeros, which is kind of why it works. Now check this out. This row comes this column, this row comes this column. You've got the same first row. Is that clear enough? Same first row. Look at the second row. It should be twice the first plus the second. That's going to be 6 minus 4. Twice the first plus the second should be like a 4. Okay, I'm still matching. Now it should be 5 times the first minus 2 times the second and 1 times the third. So that should be 15. That can be minus 10. And 5, which is 5 minus 2 is down back down to 1. So I'm still good. Notice Fred hadn't come into play yet. I'm good to go right there. Ready? Now let's see what happens with Fred. 0, 0, Fred times 0, so it didn't matter. 1. So I get 0. Comes the second column. 0, 0, Fred still hits that 0. And finally, the last column, 0, 6, and Fred still hits that 0. So it didn't matter where he was, he's always hitting a 0. And that's what will always happen in this kind of thing. Okay. Any questions? Yes, sir.
So it's just like another way to solve it, or is there like a specific situation?
The situation that you would use this in from a practical point of view on a test or something is when I say write the LED factorization thing back, right? But if you're like out in the real world, right? If you have a very large matrix, right, full of all kinds of numbers, writing in this factorization. So if you've got like a 100 rows and 150 columns, right? And by the way, that's actually a pretty modest size matrix, right? When they model like aerodynamics and things like this, they have systems of equations with hundreds of thousands of variables in this, right? So you've got a big matrix like this, it's full of numbers, right? I mean, if you have like a 100 by 200 matrix, right, that's 20,000 entries, right? if you write this in an LU factorization, that turns the lion's share of your entries into zero and cuts down a lot on the computation. So that's why you would ever want to do it. Right. Okay, other questions? All right, y'all have a good one, and we will see you by Wednesday.